In our previous video, we explored how to create custom symbols for components that aren't found within EasyEDA. However, these symbols lack default footprints, which are essential to build any PCBs. So in this video, we'll learn how to assign footprints to these symbols along with creating your custom footprints using data sheets. If you're not sure what a footprint is, we'll drop a link in the description that will talk in more detail about footprints and why we are using them. Anyway, first let's start by figuring out the default footprints assigned by EasyEDA for these symbols. This will help us understand the shape and the size of the component along with its placement on a PCB. To do this, navigate to Tools and click on Footprint Manager or the shortcut Alt+F. In the pop-up, we'll see all the components used in the schematic along with their default footprints. And if you look close enough, most of the components here are based on 0603 package, which is incredibly small. But let's not break our heads with package numbers. Let's first try to understand how the footprint manager works and how we can utilize it to make the PCB development process much easier. Maybe in a different video we'll discuss more in detail about how the component packages are named and how to select a suitable one. On the left pane, we have a list of all the components used in the schematic editor. The top and the bottom pane illustrate how the symbol and the footprints are linked. Finally, the rightmost pane provides option to search for footprints within EasyEDA or footprints contributed by other users. To assign a footprint to a symbol, simply select the component and double-click on the desired footprint. It's that simple. But what if you want to create a custom footprint and use it? Well, that's easy too. Close the current window and navigate to File, New, Footprint. This will open a new tab with tools for building a custom footprint. If you're a beginner, I recommend watching our PCB stackup video before using these tools. It provides detailed information about PCB manufacturing and why we design footprints or PCBs in certain ways. The first step in building any footprint is to check the data sheet and understand the type of component package we'll be using, along with its dimension and shape. In this case, if I open the IP5306 IC datasheet, the first page reveals that the IC is based on ESOP8L package. A quick Google search will lead us to the IC package wiki, which explains the difference between SOP and other available IC packages. We always encourage you to dig deeper to better understand why these packages are named this way. However, these values are not standardized across manufacturers. Therefore, I always recommend checking the datasheet instead of blindly selecting a footprint for your IC. Now, returning to the datasheet and scrolling down, we'll find the package dimension suitable for your IC. But remember, this is the dimension of the IC and not the dimension of the footprint. Not all the datasheet provide the dimension for the footprint. So we have to slightly modify this dimension to make a good footprint that has enough space to solder as well as place the component. I know there's a lot of information on the datasheet, but we only need to focus on a few details to build a footprint. As a starting point to build a footprint, we can always start with building a pad, where the components will be soldered and then build rest of the footprint. We need to know the component's lead dimension, and in this particular datasheet, the lead dimension is separately marked as section B, with the dimensions B and C. And to find this particular value, we have to scroll down a bit to find the value for B within this table. There are two values for B, because these represents the minimum and maximum variation in the size of the lead during manufacturing. As I told you before, this is the component dimension and not the footprint dimension. If we strictly stick to these values, we might end up with insufficient space for soldering. So as a rule of thumb, we can multiply the maximum value by 1.5 to get the pad dimension. With this information, let's return to the footprint editor. To create the pad, use the pad tool and place the pad at the center of the document. This is crucial because all the measurement will be relative to the center of the document as we work through the footprint. In the object panel, you can adjust the parameter of the pad as needed for our footprint. So let's start with the layer. Since this is going to be an SMD component, set the layer to top layer only. This ensures that the pad will only reside on the top layer and won't affect any other layer of the footprint. Next, set the number to 1, as this will be our first pin. Then select the shape to match the component lead. In this case, I'll change the shape to rectangle. And finally, here we can enter the width multiplied by 1.5 that we got from the table. To determine the height of the pad, return to the datasheet and check how long the pads need to be. This is marked as L in the datasheet. Multiply this value by 1.5 and enter the result in the object panel. Once we have one pad, we can quickly replicate this for rest of the pads by copying and pasting them at a distance E marked on the data sheet. In our case, it's 1.27 mm. Here we don't need to multiply that value by 1.5 as these measurements are taken from the center of the lead. To ensure the accuracy of the placement, you can always use the object panel to set the precise distance between the leads. Now we have successfully built 4 pads on one side. Now we just need to replicate this on the other side as well. To determine the y-axis distance, return to the data sheet and look at the capital E value, which indicates the distance between the leads vertically. I will reduce the E value slightly, at least by half the L value, because EasyEDA calculates the distance from the center of the pad. This completes the 8 pads needed for the footprint. There is just one final ground pad left to complete. To determine this value, return to the data sheet and use the E2 and D value to create the pad. Also ensure the pad is centered. Once the footprint is done, I usually use the measurement tool to double check the footprint dimension with the data sheet, and I highly recommend you do the same. Once you are happy with the footprint, go to the pads and number them accordingly. We can stop the footprint at this point, but to make the placement of the component during assembly easier, we can use the silk layer to draw the outline of the component. Also, we can draw a small notch using the circle tool near the pad 1 to indicate the first pin. This process of silk layering is just for aesthetics and does not play any major role in electrical properties of the PCB, so it's up to you to design it however you like. Anyway, once you're happy with the footprint, you can save this custom footprint and give it a name. Just like the symbol editor, the footprint is saved globally and is not visible under the project folder. To access that, we need to go back to the schematic editor and use the footprint assignment window. You don't have to keep up with the following steps. I just want to show the difference between custom footprint we built and the footprint that was default within EasyEDA. As you can see, they look very similar, but with slight variation in the size of the pad because we took the multiplication factor 1.5 arbitrarily. And also because the silk layer looks much better with the notch on the default footprint. Anyway, this concludes the video. You can follow the same process not just to build IC, but also to build any type of component you would like using EasyEDA's footprint editor. In the next video, we'll see how we can convert all these connections and the assigned footprints on the schematic into a printed circuit board. So make sure to like this video and be subscribed to our channel. If you have any questions or doubt, don't hesitate to drop them in the PCBcupid Q&A section. Until our next video, keep learning and keep creating.